Good afternoon and welcome to our 19th annual exhibit of hydrogen and fuel cell technology. We're inviting you to sit down and have a drink. The drinks are on the house. We'll be serving not cocktails but Coca-Cola and coffee and discussing the innovations in the fuel cell industry. With us today is a new topic. We're going to fly. We're going to go up in the air. We'll be talking with Dr. Josef Kallo, who's from Deutsches Zentrum für Luft und Raumfahrt. That is aeronautics and space flight. And we'll be talking about fuel cells for aeronautical applications. Please welcome with me Dr. Josef Kallo. So, good afternoon.
Hi.
This is the first time, actually, I've done this. Yeah, you've been here before, but it's the first time I've actually talked about the aeronautical applications. So I'm fascinated. The first question that comes to my mind is the particular problems. I understand that you use PEM cell technology. PEM cells are really fussy things. They like to have a certain infrastructure. They need a steady flow of gas. They need a steady flow of humidity and so on. So they are reliable but fussy ways of getting energy. What are the particular challenges of using PEM cells in aeronautical applications?
So first of all, the fuel cell application known from the mobility technology, they are made for on-ground applications like cars, like forklifts and so on. So in that, we have a partial pressure of oxygen of around 200 millibars, which is normal on ground. Mm-hmm. So the total pressure is around 1 bar. Mm-hmm. Going into the air, we have to take in account that the air pressure is decreasing with the altitude. And with that, we go to partial pressures of oxygen down to, let's say, 0.1, maybe lower. So the question was, can a fuel cell work with that lower pressure? So from the electrochemical part, the fuel cell can work with that very well. Mm-hmm. The losses are very low. But there is one issue, and that is the relative humidity. PEM fuel cell, they need water for the conductivity. They need water in the cell itself. Mm-hmm. So the water uptake capability of low pressure air is higher than on ground. And we had to deal very well with that question. Mm-hmm.
Was this something that you discovered once you got involved? There are some people who go climb a mountain and discover only once they're up there that they can't boil an egg because water boils at a low temperature. Did you people expect this was going to be a problem?
Yes, so we expected that this is an issue, but directly we took a closer look in the correlation between temperature and pressure, and we can say that we can drive a fuel cell down to 0.6, 0.7 total pressure bars, total pressure without issues at the moment.
Would you know offhand what altitude we're talking about generally if we're at that pressure level? How high?
Yeah. So we have two applications. The first application is the fuel cell for propulsion. We have the Antares DLR H2, which is a motor glider. And in that application, we expect then we can go up to 4,000 to 4,500 meters. That's the relative pressure for that. Then we have the second application, which is the APU replacement for the A320 aircraft. Wow. And therefore, we have a very special condition. The pressure in the aircraft, in the A320 aircraft, is lowered normally to 0.8 bars in flight. Mm-hmm. And with that pressure, we can operate the fuel cell even in very high altitudes. Mm-hmm. So for commercial aircrafts, we can use the air from the climate control unit, even in cruising altitude at very high altitudes.
Whenever I think of flight, I always think of how much extra money I have to pay for my heavy luggage. they charge you an arm and a leg for this. Aircrafts really are designed to be light, and it's
Yes.
very important for them to be as light as possible. It makes taking off relatively easy and landing safe. Was it difficult to scale down the weight factors involved in using PEM cells?
So first of all, in an aircraft application, we have two parameters. The first one, the weight. The second one is the efficiency. So if you have to take a lot of fuel into the aircraft, that's also weight. So system weight and fuel weight is very important. For the system weight, we worked together with a cooperation partner to develop a highly integrated system. And also the system which was integrated into the Antares DLRH2, it's a very highly integrated system with a cooling loop. So therefore we had a very lightweight system. And the second part, the efficiency which we drove in the last flight was over 50% from the lower heating value of hydrogen. So in total, we can say that we have a very high efficient aircraft and a lightweight system.
I suppose the next question, if we go through the list, it has to be, of course, lightweight. There's enough people on the Earth who have a phobia of flying. You are like 10,000 feet in the air at certain moments. So how safe is this technology for example, in passenger travel?
So in this application, safety is the major point. So without certification and rules and regulations, nothing works. So just to give you an example, for the first fuel cell system for the A320 aircraft, we had a 4 years pre-qualification time. So in that time, we had to assess a lot of safety chapters from the aircraft industry and to develop a system which was coupled with more than one safety systems. In the second system, in the Antares DLRH2, we have the EASA rules, CS22 to be exactly, which deals with propulsion systems in aircrafts, and we not just tried, but we are now EASA 22 qualified.
I shouldn't put you on the spot with this question, but I can't resist. It seems to me that just recently, one series, a particular type of plane whose manufacturer I won't mention, had problems with its batteries and had to land because there was smoke in the cabins. And this happened not once, but more than once, to the point where they had to ground the whole series. Stuff like this doesn't happen to you, does it?
Yeah, fortunately we didn't had such issues, but just to give you an impression how important it is to take care of every screw and every, let's say so, every parameter. We had once a point when a bee, which is normally in the nature, just went into a free hole, and then we had to replace the whole system because the bee was transformed in very small pieces and put into the whole system. So just to give you an impression, therefore we had to change the complete system to build it in pieces, to clean it up and build it together. So we take this very, very seriously, and it costs a lot of money.
Well, I can identify that because, of course, there was a plane that landed safely, although it was a crash land over the Hudson. I'm a Canadian, and these were Canadian geese. And it just takes one of them to mess up one motor, so it is an issue. When we talk about, I mean, you're describing two different applications. One is utility power on board of a large passenger plane, and the other is a plane that actually flies under power using a fuel cell. And that fascinates me itself. First of all, because it addresses the questions of how much energy can you store? What is the range, for example, of this glider which you power with hydrogen?
So in the first version of the Antares DLR-H2, we had something around 5 kilograms of hydrogen on board. And we are using this storage system at the moment to qualify the fuel cell in flight. In the second generation of the airplane, we will have something around, I would say, 12 to 15 hours of flight time. And in the over next generation, we plan to have something around 30 hours, 30 of flight time.
And of course, flight time is one way of measuring the range. The other would be distance. So how far can you go?
I think we can take the challenge to go more than 1,500 kilometers in one piece.
In one piece?
Yeah.
Okay. When we refer to fuel cell technology, many people are surprised that fuel cells also get married with other systems. For example, there are niche markets where the combination of batteries and hydrogen fuel cells make perfect sense here. But you've got a very unique approach to the combination of batteries and fuel cells for your glider. Could you tell us how that works, the combination of batteries and fuel cells in that unit?
Yes, so for the aircraft application, we have more than one phase. So in the first phase, we have the taxi on ground, which we need maybe 10% of the whole power of the aircraft. Then we have the take-off phase, which needs a lot of power, which needs the peak power. And this has to be very safe and reliable power. And then we have the cruise phase, and then the landing. So the interesting point is, first of all, for the takeoff phase, we have a so-called direct hybrid in which lithium-ion batteries can be coupled with the fuel cell. So then we have two sources of energy for the takeoff phase, and we can double the power which we can use for the takeoff, so we can climb much faster. And therefore, we had to develop, as I said, a direct hybrid, which is a combination between a lithium-ion battery and a fuel cell. And the special thing with this is we do not use electronic converters or software to channel the power from the battery or from the fuel cell. It's the architecture of the battery and the fuel cell which drives the power sources.
I find this an interesting application. Some people are aware already there are things like forklift trucks that use batteries and fuel cells. Basically, they're optimizing the battery by not allowing it to completely discharge.
Yes.
And not overcharging it. You've opted for another application which says at one time we want demand to go up to 100%, the maximum output of the fuel cell and the batteries. Now, for me, the interesting question is, some people would say, why not 100% batteries? You would have to double, perhaps, the quantity of batteries on board. Do they get too heavy? Or the other option, why not 100% fuel cell powered? What are the drawbacks of having a 100% fuel cell? Why is this marriage so perfect?
Yeah, so first of all, if we take only batteries for that energy quantity we have on board, I think we had to triple or maybe 3.5 times to have 3.5 times more weight on board than we have today with the fuel cell, which doesn't allow to have the range. That's the first thing. The second thing is we can refuel very, very fast. So in maybe 15 minutes, we can refuel the plane.
Wow.
And we can also recharge the batteries also in flight. So we can use the airplane during cruise, and if we land, we have the battery maybe at 60-70%, then we recharge the battery to 90%, and then we can start very fast again. That's one point. The second point is, and this is typical aircraft thinking, we have two completely different power sources on board. The battery and the possibility to have a fault in the battery system is completely different to the fuel cell system. we are calling this dissimilarities. So the systems are so different that we do not have the same fault in both systems. So the possibility we have then is, if one system fails during takeoff, we can go to cruise with only one system. And this is crucial for the safety of the airplane. This one point. Having only the fuel cell on board, that will be nice, but then we had to carry a lot of fuel cell power with us, a lot of investment with us, without using that during cruise. And the combination between the battery power, low energy content, and the high energy content of the fuel cell with the hydrogen, with lower power, is ideal.
Of course, when it comes to looking for clients for such a device, the first question would be how expensive. And here I can refer to one of the problems, the difficulties we run into, for example, for automotive applications. You can produce a fuel cell car and they are lovely to drive, they're silent, they're green, and it's wonderful, but they might cost you $50,000 or $100,000 per unit minimum. So they are lovely, but they're very expensive. Yes. And there's not an infrastructure to fuel them yet. So there is this cost factor involved. How does that play out for your applications? Are you more expensive? Do you have a competitive edge with the technology? How does that work out?
So, to be direct, the difference between today's prices for aircraft systems and fuel cell price is in the aircraft application not so high as it is comparing an internal combustion engine with a fuel cell in the mobile application. And I think this could be a door opener or a first application to use a fuel cell in the aircraft region, in the aircraft industry. And just to give you an impression, this is not for the commercial aircraft. In the commercial aircraft application, we have to bring also 10,000 of hours of durability. But in the Antares DLR H2 application, the time between overhaul, TBO, is normally in that region something between 1,500 and 2,500 hours, which is today for a fuel cell, no, it's not a problem, even in aircraft conditions. Yeah. And we are, let's say so, we are willing to pay for a motor, for aircraft type, Antares type, we are willing to pay a couple of $10,000s. So with that, we are very, very near with the fuel cell price to the price of a normal internal combustion engine. So there is no high difference. And with that, we are very near to the application.
So it sounds like it's kind of like paying for leather seats for a good car, a little bit more expensive. But we perhaps do have time for one question from the audience. If there is we have one question.
Yes, it's a fascinating topic. Maybe one question on the APU application that you have been doing for Airbus. Which hydrogen storage technology are you using for that application?
So for our application, we used for the A320 test, we used pressurized hydrogen, 350 bars. And for the actual application, I have to pass this question to Airbus.
But there's more information available here, certainly. If you want to continue the conversation, Dr. Josef Kallo from Deutsches Zentrum für Luft- und Raumfahrt is available right here. His booth is C66. Dr. Kallo, it's been a pleasure talking to you. Thank you very much. Hope to see you back here next year.
Perfect. Thank you.
Bye-bye.
Bye-bye.